the first couple of problems are multiple choice questions. They're based off of the part of the unit where we did experimental design. Right? So definitely have a look at those notes before next week. According to a political scientist in the United States, women are more likely than men to vote Republican. All right, it's an academic problem. I don't honestly know if that's true. The political scientist selects a large sample of registered voters, both men and women, and asks each person sampled whether they voted Democrat or Republican in the last election, which of the following statements applies to this situation. So we have first possibility, it's an observational study with no treatment. You have, it's an experiment, right? Establishing cause and effect. The response is gender, and the explanatory variable is political party voted for. And then the last one, well, in no particular order. A small sample would have been just as good as a large sample and much less expensive to collect. All right, so those are different possibilities. Just going back to it, the scientist selects a large sample of registered voters and asks each person sampled. Right, there was no treatment imposed. Right, if there's no treatment, it's not an experiment. All right, so no treatment equals not an experiment. All right, there must be a treatment in order for the study to be considered an experiment. Right. So it's looking like option one here, but you also take a look at the other ones to make sure. The option three, really, we don't consider cost when deciding what an appropriate study would be. That comes kind of after the fact. Once you decide on the type of study you're doing, then and sampling and whether or not the population sample size is sufficient, then you start getting into cost, right? But that's not really the case here, so we'd eliminate that one. And the response is gender versus the explanatory variable is political party voted for. That would establish a cause and effect relationship, right? Explanatory response variables typically correspond with experiments, but you can make a case for it in an observational study. But here, they're asking individuals, right, so both men and women, whether they voted Democrat or Republican in the last election. Right? So that doesn't mean that we're going to establish a causal relationship between the two. Right? Just because it turned out perhaps that more women voted Republican doesn't mean that the political party causes the gender. Right? You can't say, all right, well, the person voted Republican and they must be female versus male. So that one is not true. Right? Not necessarily true. That's the tricky thing about some of these multiple choice questions. We're not always looking for 100% true, 100% false. We're looking at what is more likely to be true. Right? It is true that this is an observational study because no treatment was imposed. Right? So now, if just think about the ways in which I could impose a treatment. Maybe me as the person doing the polling would go up to a person wearing a red tie, which is typically symbolic of the Republican Party, or a blue tie for Democrat, and then ask the question. So kind of giving the person a clue as to what my potential party affiliation would be, then they'd look at it and maybe that would influence their decision. So you could have a controlled experiment in that regard. You would need the control group, though, the one where there's no treatment being imposed. But there's no treatment in this design, so it's an observational study. Now this one, I apologize, I didn't number them on the form, so I'm just going to have to say the next one instead of like number 2. Experiment is carried out on 30 male cows. 15 of the cows chosen at random are given an energy drink, which sounds kind of horrible, while the other cows, 15 cows, maintain their usual diet. So there's definitely a treatment being imposed here, and that is the presence of the energy drink. all of the cows then run through a maze. The cow who had an energy drink ran the maze in a mean time of 37.2 seconds, while the cows who did not had a mean time of 41.3 seconds. Are the numbers, so after all that, it's asking, are the numbers parameters or statistics? All right, so parameters apply to population. Statistics apply to samples. All right, so 15 of the cows chosen at random, all right, and then the other 15, I guess. But this is not the entire population of cows. So in either case, whether it's the ones that got the energy drink or didn't, we're not dealing with parameters. In inferential statistics, what we do is we use statistics to draw conclusions about population parameters. But in this case, they didn't tell us anything about what would be typically the case for a cow on average. Right? So if they said something like, a sample of size 30 was carried out on, an experiment is carried out on 30 male cows, which is a sample of a population whose average time through a maze is this, then that would be a different story, but that's not what they said. So any instance in which they said parameter, we toss. They're both actually statistics, all right? And, I try to keep the problems on the test consistent. I mean, the topics associated with the problems on the test consistent with what's in the review. So the question number 2 on the test will ask you about whether or not a value is a parameter or a statistic, all right? So if you have that idea, statistics correspond with sample values, parameters correspond with population, then that should get you. I mean, it's not designed to be a terrible question. So hopefully take good notes and we go from there.
So parameter is part of this? A stat?
A parameter is a measure of the population.
Oh.
So an example would be like if I say the population that I'm referring to are all students at WCC. Then I could say, okay, the average grade that any student at WCC earns is a B+, for example. I don't know. That would be a parameter. But if I were to just say this class here, which is a sample of the students at WCC, that would be a statistic. All right. I guess I could just number them as I go. 1, 2, 3. Right. So polling company wishes to send interviewers to conduct a survey of households in North America. They decide to conduct a simple random sample. Remember, a simple random sample is when you put all the names of whatever the population is in a hat, figurative hat, and then randomly, like literally just shuffle it all up and just reach in blind, pull a name out. That's one element of the sample, another, and so on, right? That's a completely randomized approach, right? It's the least biased approach to sampling, right? Because you have no control over the items that make it to the sample, right? Which of the following are reasons why this type of sampling is inappropriate, right? The first one, a list of households in all of North America is not practical to maintain. Absolutely, right? That would make it very challenging to put a list of all the names of all the households, or, addresses, whatever, in a hat and randomly select. Right? If you can't get the list to begin with, how can you sample from it, right? And then also you start thinking about like, all right, what's the definition of a household? You're talking about like a studio apartment, or does it have to be like a physical house? Who knows? A lot of stuff that's kind of left out of this. The cost of sending interviewers to the widely scattered households in a simple random sample would be excessive. Yep. If you had decided that you're going to do a simple random sample, then you start doing a cost analysis and say, wait a minute, I got to send an interviewer to every single household that's in my sample, and that sample is randomly selected. from North America. All right, so I could have one household in Washington State, like 3 households in California, 5 households in Texas. I could find myself all over the country. I mean, is that something that's doable? Who knows, right? So I would say it would be excessive. So we could include that one. Every member of the population does not have an equal chance of being selected for the sample. That actually is almost a definition of a simple random sample, right? If you take the words does not, or, just kind of change this part of it, does not have, to has. If every member of the population has an equal chance of being selected for a sample, that is a simple random sample, right? It's completely unbiased, right? And there are drawbacks to simple random samples. And one of those drawbacks is the fact that it could over account for certain areas. Like, for example, if we're going North America, technically, if I were to do a simple random sample of, let's say, 500 households, it is possible, based off the nature of randomization, that every single one of those 500 households could be located in New York State, right? That wouldn't be representative of the population, but that is an unbiased sample. It's when I start imposing conditions like, all right, I want 500, but I want 10 from each state. Then we're talking about a stratified random sample, right? Each state being its own stratum. Right. But since this is saying the opposite of the definition of a simple random sample, and they're telling us it is a simple random sample, I would toss this one. The sample does not represent the population. I can't say that's definitely false. It may not represent the population, right? My example of I'm sampling from the United States, and all of the places that come up in my simple random sample are from New York. That would be an instance where it doesn't represent the population, but it's not guaranteed. So that would not be the reason why it was inappropriate. That's not an ideal situation, but it's not a reason to toss the concept of a simple random sample. Otherwise, nobody would ever do it, right? So that one would be out. And also, you go by the Roman numerals. We already said yes to 1 and 2. There is no choice that says 1, 2, and 4. So you can kind of go that route too. But that would be the answer. All right. So number 4, police officer wants to know whether banning chewing gum from public parks is a good decision. So she puts up a big ad in the newspaper asking people to log into her site and give their opinions. What is the bias inherent in this survey? Right? Anytime you have voluntary response, it's automatically a voluntary response bias situation. She put up the ad in the paper, and then the individuals, without being selected to do it, they self-selected. They chose to participate in the study. That introduces voluntary response bias. Right? Anytime that happens, it's like those polls. You're reading an article online, and they'll throw a poll in there, and then it'll say, which of the following do you agree with? And it could be really anything. It could be politics, sports, medicine. It doesn't really make a difference. But the fact that you chose to participate in that study without being asked to, even though it's kind of implied that they wanted you to, you individually were not invited to participate in that. You weren't randomly selected. So it's logical to assume that other like-minded individuals, and let's say it is politics, because that's pretty divisive. So who are the people that are most likely to participate in a political survey? People who have strong opinions one way or the other, right? So, sports is a little bit different, because if somebody put up a poll that says, do you think that insert New York team here is a good team? Like, you go by the numbers. I mean, the Giants are 4-8. You can't say they're a good team. Jets are in the same situation. Other teams are in the off season. I mean, the Rangers are good, but they just got blown out on Tuesday. So, that's not like the world-ending sort of thing, because there kind of really is a right answer there. But when you get into opinion polls, that's when things get a little dicey, or legitimate opinion polls, I'll say. All right. Already lost count. Number 5. There are 300 freshmen and 200 sophomores at the school, whatever school we're referring to. You randomly select 12 freshmen and 8 sophomores to obtain a sample of size 20. What kind of sampling is this? Whenever you take your population and break them up into groups and then pull a smaller sample from each of those groups, you're looking at a stratified random sample. All right, so that's the categorical sort of approach where, you know, even the North America example, I could categorize as each stratum as a state. Every state represents a stratum. And then I randomly select 10 from each state, put it all together into my sample. That's going to be a stratified random sample. As opposed to a cluster sample, which really kind of starts off the same way as a stratified sample. You break your population up into different groups, and then you randomly select an entire group. You don't pull from each one individually, you just pull an entire group. Right? So it starts off the same way, but it kind of ends differently. Right? Yeah, it's definitely not simple random sample, because if it were simple random sample, you would have all 500 names in a hat and you just pull the first 20. All right, that's not what happened here. Convenience sampling. Convenience sample often confuses people, because it really is basically whether or not the sample that you obtain is convenient, right? And that could have a lot of different definitions, right? So if I wanted to get an opinion, student opinion on policy at the college, I might say, oh, you're all in front of me, show of hands, how many people think this? And maybe you're a representative sample of the population. You don't really know, but you sure are convenient. You're right in front of me, right? It's the same idea of like a person that does if you're walking through the mall, every now and then somebody will come up to you and say, hey, can you participate in a brief study? And you say no, and you keep going because, you know, like stranger danger. But it is possible that people stop and participate in the study. So now you have convenience sample, you got voluntary response. There's all sorts of things wrong with that, right? The systematic sample is the case where you assign a numerical value to elements within the population, and then you randomly select a number, and that's the value you pull. So if I have 500 people here, I might randomly select a number between 1 and 10. Right? Let's say the number 7 comes up. So I would include every 7th person in my study. Right? So 1, 2, 3, 4, 5, 6, 7, you're in. 8, 9, all the way up to 14. 14, you're in. 21, you're in. Right? Multiples of 7. That would be systematic. Right. Number 6, sample of students from school was taken by choosing the first 100 students who arrived at school to respond to a survey. That would be convenience sample. Right. If the phrasing of it were changed slightly, instead of saying by choosing the first 100 students, if it said you would choose every 100th student, right? So person number 100, you're in. Person number 200, you're in. 300, then that would be systematic. Stratified, simple random, that wouldn't really apply here. There's no analog to that. An ordering question. I like these kind of questions because, you know, the answer is right in front of you, and if you just kind of look at it logically, you'll be able to fairly easily get this. This particular question involves a stratified sample, but I could give a question where it's not voluntary response. That would be ridiculous. Actually, it would be kind of fun, because I don't know how I could ask a question about voluntary response and not have in the process somebody volunteering to be part of it, which would just kind of give it away. Yeah, we'll see. I'm still in the process of revamping the test. But let's say I did a systematic sample. I might say something like, count up the number of individuals in the population, randomly select a number between 1 and 5, whatever that number is. Count off until you get that person, and then count off again and again and again, and then put all those steps in order. So it could be something like that, right? So it's all kind of fair game. Let me just read through the options here, or the steps. Stratified sample again, so that's the one where you have your population, you break them up into groups, you pull from within each group, and then you compile it all into one sample. Right, so we have select a simple random sample from each separate group. Well, probably not if we haven't created the groups yet. Find a list of items. Divide the population in separate groups. Right, so in order to divide a population, we have to have a population, and then conduct a survey and collect the data. All right, so the first thing that we would have to do is find some sort of list of items. So that would be my first move. Right, something that I could actually break up based off of whatever the predetermined criteria are. Right, so I have my population, my list of items, that's my population. Right, and so right there we can just eliminate two choices. Then I would divide that population into different groups. All right, so we already know the answer has got to be the last one, but let's continue on. Select a simple random sample from each separate group. That would be my third move. All right, so I took my population, I had a list of everything, broke it up into the different categories, and then pulled from within each one. And now what I have is my sample. What would I do with my sample? I would actually apply the study. I would collect information. All right, so that would make this the last step in the process. All right, so the first 7 questions, I know it's kind of a weird number, but the first 7 questions are all going to be those fact-based scenarios associated with experimental design. Right? There's another one down the line, but it has a lot more oomph to it, so I kind of saved that towards the end. Right? But then we get into the computational questions. Right? This one is talking about a normal distribution. All right, so, I mean, aside from the fact that it just says it right here, we're asked to find a percent of the population or a probability or an area, right? That's usually a key indicator. So a well-known standard IQ test produces normally distributed results with a mean of 100 and a standard deviation of 15. Numbers are really clean, so you know it's a made-up problem. What percent of the population have an IQ, I guess, it's multiple people, have an IQ between 91 and 109, right? So there's a couple different ways that you can do this. It's something that you could do entirely on the calculator, which a lot of people really like. So I'm just going to get into the notation a little bit. We're looking for the probability that there's some value that's between 91 and 109. Right? And because it's a normal distribution, I would use the normal CDF function. I forget if it's norm or normal, but it's in your probability distributions menu. I'll just make a little note here. So toolbox, probability distributions, normal, and it's the norm CDF. Well, norm CDF range because it's an interval. All right. So for a norm CDF range, you have 4 components: the min, the max of your interval. So we'll call this the min, the max. The mean, and the standard deviation. Actually, let me stay consistent here. And standard deviation. All right, typically related to a population. So I use the mu and the sigma. Well-known standard IQ test produces normally distributed results. It sounds like a population. Right? It didn't say that this was a smaller sample of a population. It just sounds like, in general, this IQ test has a mean and standard deviation of 100 and 15 respectively. So in my calculator, I would put in 91, 109, 115. And that's going to get us about 0.451, 4515 really, but the closest one to that would be this guy over here. So they put it in percent form, and slight difference in rounding. That can happen. I try to avoid it, but sometimes it happens because depending on whether the answer was obtained using tables versus a calculator, it could have a slight impact. But generally, we look for the closest approximation. Now that contrasts with the next one, which talks about a group of individuals. So this is saying, what's the probability that the mean score of the 4 students will be 28 or larger, right? So just to get the notation in there, we're saying the probability that X bar is going to be greater than or equal to 28, right? Certain standardized test, we know the mean score, standard deviation, right? And we know the sample size. So this is central limit theorem, CLT. And what you need to know here is the mu sub X bar value and the sigma sub X bar value. All right. Now this is a central limit theorem question because we're given a sample size and they're asking us about a mean score. All right. So to contrast that with the one that came before it, that one didn't ask us about anything more than just a single individual from the population, right? Not a group of individuals, right? And it also asked what percent of the population has an IQ between these numbers. So it's saying what's the probability that an individual value would be between 91 and 109. Whereas in this one, we're looking for the average of a group, right? Now, mu sub X bar, by definition, is equal to whatever the mu is, and sigma sub X bar is sigma over the square root of n. All right, so what we can do is, well, that, because they told us the mean score is 25, so I know my mu sub X bar is 25, and the standard deviation is 5, so 5 over the square root of 4. So again, you know it's a made-up problem because the numbers are nice. Right? Square root of 4 is 2. We're looking at 2.5, 2.5 if you want. And I'll just make a little note of that. So the way this differs, I suppose, from the previous example is we're still going to use norm CDF range. Right? Norm CDF range, we're still going to go with the min, the max. Let me just kind of smidge this over a little bit real quick and turn that off because it'll take the actual question with it. Then the difference is that we put in the mu sub X bar and the sigma sub X bar. So 28 is my min, because if you're going to be greater than or equal to it, you're gonna start off with that number 28. You're going to go to something large. All right, and I'll go through it in a second, but it's generally arbitrarily large as long as it's large enough. How large is large enough? You don't know until you do it, right? Then the 25 and the 2.5. All right. So again, I'm in the toolbox, go to probability, distributions, normal, and then norm CDF range. I'm going to put in my low bound, 28, my upper bound, something large, 100, I guess. Then 25, then 2.5. Lock it in, hit OK. And you get this number here, which amounts to about 0.12. So we have an answer. Right, but then it begs the question of, okay, did we go far enough? So maybe that large number wasn't large enough. Who knows? So what I do is I change it to something even larger, right? So I'll make it 1,000. If there's no change in the decimal, then it's large enough, right? But if I did something like, let me just do it. Get out of here. Let's say I only did like, I thought 30 was large enough. See, you get something that's not even really close to the right answer. Although if you have it in your mind that whatever you get in the calculator, you're looking for the closest choice, in this case, you actually still would have gotten it right, but we don't want to rely on that. So go big and then go bigger and see if there's a change. And if there is a change, go even bigger. Keep going until there's no change in the decimal. Right. Usually if you go fairly extreme, like 1,000 off the bat, you're okay. The thing is, if the question said, what's the probability that the mean score of these individuals will be 1,000 or more, then 1,000 is not big enough, right? So it's got to be relative to the summary values that they gave you. All right, number 10, this one, and like I said, I mentioned this before, I'm going to keep it consistent in the type of question that's being asked. The topic of the whatever questions in the review is the topic that'll be covered on the test, right? So this one is asking for the p-value for a hypothesis test, but maybe I'll ask for a test statistic, right? So you know, this one's match pairs. Maybe it'll be independent samples, all right? So I could change up the test, but the flavor of the problem is going to be similar, all right? So a food company claims that a diet product it makes helps people lose weight. The following table shows the weights of 5 people before and after using this diet product. I lost my place. After a period of time suggested by the company, an inference test was conducted at the 1% significance level to test the claim that the diet product is effective in helping people lose weight. Which of the following is the p-value of this inference test? All right, so if you have before and after, that's a match pairs t-test. All right, we need the differences between the values, but we could let the calculator do that, or we could do it manually. The numbers are nice, so I'm inclined to just kind of scratch it out on the bottom, but maybe the numbers won't be nice. Who knows? So I will put it into my calculator under statistics. All right, so this is like a blast from the past back to Unit 1. So statistics, we can enter our data, 120, 150, 140, 135, and 130. Then the second column, 125, 130, 130, 140, and 120, right? So I'll just make a note at the bottom here, I guess. So we're saying input before in value V1, and after goes in frequency, abbreviate that, frequency N1. Then go to, I'm not going to overdo it with the quotes here, value V2. V2 is what I said. Hit OK. So I'm going to go to value V2, hit OK. I'm going to select fill with a formula. Empty. And I'm going to type in V1 minus N1. All right. And, it's a little bit of a hunt and peck kind of situation. But if I look at this, I can see the alpha key, lowercase, uppercase. And I have V over here, N over here, right? Minus is minus, so we're good there. So what I'm going to do is hit Shift alpha, then division symbol to bring up a capital V. Type in the 1 minus Shift alpha 8 to bring up the N as a capital, and then a 1. All right. When I hit enter, enter, wrong calculator. Hit OK, it's going to find the difference between every value in V1 and its corresponding value in N1. All right. So that's a good thing. Maybe not so much in this case, but in the case of, like disgustingly lengthy data sets, like lots of decimals, lots of values, then there is a benefit to doing it this way, right? At least having it down on paper, because when you're referencing it during the test, you want to have as accurate information as possible, obviously. So I'm going to hit OK, puts those values in, which is great. I need from here, I need the mean and the standard deviation. All right. So the N value is 5. The calculator will tell us that anyway, but there's 5 pairs of values here. All right. So, and you can even see the person 1, 2, 3, 4, 5. So there's 5 values. I need the X bar value. We call that X bar with a subscript of D, and S with a subscript of D. D stands for difference. All right, so D stands for difference. So I go into my stats tab here, and for the blue column, I want the mean, the sample mean, which is 6, and the sample standard deviation, which is 10.83974. I'm just going to grab the entire decimal. All right. That's all the background work that needs to happen before we could actually use the inference app. I'm going to do it here. So go to inference. So you see that as an app. Tests. One mean. T-test. All right, so T-test we typically use for small samples unless we have a reasonable, I would say expectation, I guess, but we can reasonably assume that the population is normally distributed, right? Or the population standard deviation. Here, they didn't really say anything about the population itself, right? We don't know if it's normally distributed. We have a very small sample size, and we don't know sigma, so that automatically puts us into the t-test category. All right, so I hit OK on that. The null and alternative hypotheses, if I were actually conducting this hypothesis test, my HO would be that there is no difference, and the HA would be that there is some kind of difference. They're saying that the diet product is effective in helping people lose weight. All right, so as a default, I would say that there is no difference. As an alternative, if you lose weight, it means your weight before is greater than your weight after. All right. So if I were on a weight loss plan, which probably should be, you have a weight that you start with, and then after a period of time, that new weight should be less than what you started with, right? So what you started with should be greater than what you ended up with, right? And then, you know, like depending on the context, that might change things, because in this case, a decrease is showing improvement. Whereas if you're talking about like how much money you earn on an annual basis, you want the money, you know, the dollar value after to be bigger than before, right? So that would be a less than situation, right? So what we do for this is we put in, it's really based off of the alternative notation here. This is the same as, oh, watch, oh, okay, I thought the pen died. Mu1 minus mu2 is equal to 0. And this is the same as saying mu1 minus mu2 is greater than 0, right? So in my null hypothesis, I'm just going to put in a 0. My alternative, I'm going to make that a greater than 0. The notation doesn't perfectly line up, but it's basically like you have a left-hand side that's in symbolic notation equals 0, left-hand side greater than 0. So as long as it has that same structure in the app, you're good. Then you go to next. I got to put in my sample information. All right, so I have a 6, a 10.83974. Sample size is 5. Significance level, they told us alpha is 0.01. They said 1% level. So I put that in. All right, so basically everything kind of fits into a spot, you know, so as long as you have your information, you should be able to slot it in the appropriate location. Then you go to next, and it tells us the t statistic. So I'll make a little note here. You have your p-value, and you have your test statistic. All right, the p-value is 0.142-ish, and the test statistic is 1.238. Degrees of freedom is 4. We didn't really care about that. As a multiple choice question, you know, it's not necessary to do all this stuff, like all the little notations that I'm making, but you know, you want to be prepared for the free response also. But you look at the choices and you see that one of them, you know, it's kind of mean of me, I guess. One of them is the test statistic, right? So if you don't know the difference between a p-value and a test statistic, I'd say that's probably an issue because, you know, because it says it right there, test statistic, and it says p-value right there. So like, if you're in the right test, then it's almost impossible to screw up at the finish line or trip at the finish line, right? Now, that being said, we have something that's close to, but not quite exact, but close enough is good enough. All right. So basically, I mean, we had to kind of do all the background stuff for the hypothesis test. We just didn't have to draw the graph and we didn't have to write the conclusion. All right. So in the grand scheme of things, it doesn't seem like it's much of a savings, I guess. But from my experience, the thing that people like the least about hypothesis testing is actually writing the conclusion. So it's kind of nice, I guess, to have a question that doesn't require you to go the distance. All right. I'm going to make sure to post this up, both the video and the PDF version of it later, so that you can really kind of dig deep into it. Try to keep at least some of it up on the screen while I read the next question. I already forgot, what number are we on? 11. All right. So design the study using the methods learned in class. It's actually a fairly straightforward process, but we do have to consider what is being studied here. All right. So a researcher designs a one-year study to examine the effect of physical activity and nutrition classes on weight loss of adolescents aged 14 to 17. Study has 3 levels of physical activity: none, 30 minutes a day, 60 minutes a day. 2 levels of nutrition class: none, once a week. 16 boys are randomly assigned to each combination of physical activity and nutrition class. Each study participant's body fat percentage is measured before and after receiving the treatment. When it comes to designs of studies, whether it's an experiment or an observation, I usually start with the diagram and then sort of backfill in anything else that might not have been accounted for. Right? So again, we got a lot of stuff going on here. We have 3 levels of physical activity and 2 levels of nutrition class, right? So again, I mean, we're talking about individuals being sampled, right? We have interaction of physical activity and whether or not the individual is taking that nutrition class, right? The 15 people are assigned to each, 16 people are randomly assigned to each combination of physical activity and nutrition class. So that's my first step here. We have none, 30 minutes, and 60 minutes. So I'm just going to use the numbers here as my labels, 30 and 60. And then we have the N group and the W group, right? So what's happening here is you have your sample. That sample is going to be broken up, and you can decide which way you want to break it up first, by time, then by whether or not they're taking a class, or vice versa. But I'll do it by time. So they're broken up into 3 groups. That went off the rails on me real quick. All right, they're broken up into 3 groups. We have the 0, I'll say 0 min, 30 minutes, and 60 minutes per day. Then the subset for each of those, this just brings us back right to Unit 2 when we talked about tree diagrams. That's essentially what these diagrams end up being. So for each of these time intervals, we get an N and a W. All right. So 16 boys are randomly assigned to each combination of physical activity and nutrition class, and their body fat is measured before and after receiving treatment. All right. So in the sampling process, we have our individuals. At that point, before we do anything, we would measure body fat for each individual. And we're going to do that again, right? So each of these items, each of these little subgroups are going to kind of come together. Where we would measure body fat and compare across the groups. I don't know why I thought across had 2 C's there. Across groups. The diagram should kind of give you I would say a general idea of what's happening in the study, right? We do have to kind of backfill it with the other relevant information, right? So we have a need to describe the explanatory variables, the response variables, the factors that affect the response variable, right? Any possible factor that's not under control becomes a lurking variable and could confound the entire study, right? So just kind of like quick bullet points. So explanatory variables, we're talking about physical activity, and whether or not you took the nutrition, I think it was nutrition class. Yeah, nutrition class. The response variable is going to be, you can kind of kind of coax it a little bit and say that it's percent of body fat, or you could say change in body fat. But as long as you get the idea of body fat across. All right. So the factors that could affect the response variable of body fat, you think about any other thing that might contribute to a person's body fat. You can say like heredity. You say diet, although part of the nutrition class might have something to do with that. Age, although they're kind of limiting it to the adolescent group, but on the low end or the high end, I don't really know necessarily whether that would have an impact, but it could, and I don't want to take a chance. These are things that I would want to control as much as possible. Race, sure. I mean, you could even get like kind of deep into this and say, well, time of year. We're talking, is it Thanksgiving? You just have Thanksgiving dinner or something, like you can get fun with it. And I know that there's probably a reason why the New Year's resolution is like, I'm going to exercise more this year, or I'm going to diet. It's like, what'd you do the last month and a half that makes you want to do, So like kind of an overcorrection. But as long as you get, I'd say 2 or more under the factors, you're fine. Because remember, we're not actually conducting this study. We're just kind of going through the motions a little bit. But these are the things that researchers would have to take into account, among other things, like things that I'm not even considering, like health conditions, so I'll even say that, health conditions, financial situation, like whatever you can think of, but it's really a ... Right. And so what we also include is a reasonable prediction, I guess. So a prediction of what the outcome would be. And really, honestly, we should be taking our sample of 16 individuals and randomly assigning them to different groups. The thing is, on a test, I can't really verify that you did that randomly. So I don't typically bother with that. So I would say the more physical activity, combined with taking a nutrition class, taking, will have the most positive impact. Maybe you don't need the nutrition. Maybe you already know it. You know everything that they're going to teach you, and so whether you take that class or not is maybe not as relevant. Who knows? Maybe the only thing that was missing in your life was more physical activity. But I think it makes the most sense to say that a person is more likely to be successful in this process if they have the most physical activity coupled with nutrition instruction. All right. But that's why we do the study, because, when they say something like, oh, you should exercise 2 to 3 times a week, like, where do they get that number from? Right? Probably a method like this. So I don't have 60 minutes. Is it a day or a week? Whatever. I don't even think that. Per day. Yeah. So I don't have 60 minutes per day to spend exercising. Right? But if it's a negligible change between 30 minutes and 60 minutes through this study, then I can say, all right, well, it'd be great if you could exercise for 4 hours every day. Right? Like, just live in the gym. That'd be great. All right, that's not practical. We can't do that. You'll get the same benefits if you do it for 60 minutes. Maybe a little bit of a drop off for 30 minutes, but not anything overly substantial. So give us at least 30 minutes a day. Right? Can't do 30 minutes a day. All right, well, 15 minutes a day. There's a substantial drop-off in what you could expect to accomplish if you only do it for 15 minutes a day, so that's not going to work. This is all stuff that could be determined based off of this study. We're not asked, nobody's asking you to actually definitively say what will happen because you didn't conduct the study, but you could at least make a prediction. All right, so that's what I'm looking for when we talk about the design of the study. The diagram, marked up, labeled. If I used a highlighter there to indicate what I was labeling things. If it's not obvious what your abbreviation is, then make a little key. Right? Explanatory, response variables, factors. Right? So these are, again, factors or other things that could impact the response variable aside from what the explanatory variables are constituted. And then a prediction. Right? You do those things, you get full credit.
So you just need those two.
All right, and then the last one, I think it's the last one. Yep. Number 12. In California, in 2022, gas prices were distributed normally with a mean of $5.75. It's kind of a made-up number, but it's, well, I don't know. When I was there last year and I paid $5.99 a gallon to fill up a gas-guzzling vehicle that I was stuck renting because they didn't have anything else. And when I finished paying and it was $110, I was motivated to come up with a problem to use in my stat classes that talk about how terrible gas prices are in California. So anyway, in 2023, a sample of 10 gas stations in California was collected, and it was determined the mean and standard deviation, I don't know. Sometimes I make inexplicable typos. There's no need for that word not to be there. 599 and 0.279, respectively. Assume that this sample is representative of gas prices in California at the 5% level. Test the claim that the average price for California in 2023 is more than $5.75. All right, so this is the claim that we're testing. And it's related to an average. So we're talking about a population mean. So when we say our null and alternative hypotheses, the null always involves an equal sign. This one is saying that the mean is more than 5.75. So mu more than 5.75. The null has the same ingredients as the alternative, just with an equal sign instead of the other inequality. All right. The inequality used in our alternative hypothesis corresponds in the diagram that we draw, corresponds to the tail, or tails. In this case, just a single tail on the right-hand side. All right, so this is right-tailed because of this inequality here. All right. So I need a few pieces of information. I need the critical value. We know that the alpha is 0.05. I'll make a little note of that. Alpha is 0.05. The critical value corresponding with that. We also need to know whether it's a t-test or a z-test, or, well, it's really all we've done. So it's one of those two things. So looking at the sample size, n is equal to 10 degrees of freedom. N minus 1 is going to give me a 9. All right. I know it's degrees of freedom. I know it's a t-test because the population standard deviation is not known. We do not know we don't know sigma, so we don't know the population standard deviation. If we don't know that and we're testing a claim about a mean, then it's going to be a t-test. And what a lot of people will do, and I'm not saying that you need to do this, but when you go into your inference, if you look at, you suspect it's a t-test, you go in, you look at t-test and see all the ingredients that make up a t-test. Oh, I need a mu, equals, greater than, less than, something like that. I need to know the X bar. I need to know the S, the N I already indicated, the alpha I already indicated, right? So it kind of gives you a little recipe for being able to conduct the test on paper, right? So you know what ingredients you need to find in the problem. Now, if you go into a test, you suspect it's a t-test, you go in there and the information that's given in the problem doesn't in any way really line up with what's in the app, then you're probably looking at the wrong test, right? Now, they said in 2023, a sample of 10 gas stations in California was collected, and it was determined, so that mean and standard deviation correspond to just that sample of 10 values, so that makes those numbers the sample mean and the sample standard deviation. Right. Now, I could run the whole test in the calculator at this point, but I still need to come up with that critical T value. We'll get that in a minute. But for now, I'm just going to pop this information in here. 5.75. Automatically adjust the value in my alternative. Coincidentally, the last time I did a hypothesis test, I used the greater than symbol, so it hung on to that. If I needed to change it, I hit OK and select the one that makes sense. Go to next. We pop in the 5.99, the 0.279, the sample size of 10. 0.01 is the alpha value. I said 0.01, but I meant 0.05. Sorry about that. Right, so hit OK. So I get my test statistic. So T is equal to 2.720. And I get the p-value, 0.0118. The relationship between the p-value and the alpha value is what allows me to either reject or not reject the null hypothesis. I included this in the notes, but I'll write it again here. If the p-value is less than alpha, you reject the null hypothesis. So here I have a p-value of 0.0118. The alpha value is 0.05. That's true. So we're going to reject the null hypothesis. So the null is out. Alternative is in. Right. Now it tells us degrees of freedom, things like that. So if you forgot during the you're taking the test and you're like, oh, does this one require degrees of? I don't remember. It says it right there, so you might as well write it down. Right. Then you hit OK on next. Gives you the graph, but it gives you the graph of not just, which is really nice, and it gives you the graph of not just the p-value, a little orange little schlitz in there, but also the alpha value. So we know that the alpha value should correspond to a t statistic, a critical t value that's somewhere south of 2, or I guess west. But the p-value, the shading corresponding to the p-value is well within the rejection area, right? The alpha value creates a rejection area corresponding to the null hypothesis. If the p-values area is contained entirely within that shaded region, then you would reject the null hypothesis. So you have multiple ways of verifying, right? And again, one thing I don't love about this is it doesn't tell you that cutoff for the alpha value, but we can get that from calculation. So toolbox, probability, distributions, students T, and then it's on the right-hand side. I could do TCDF. I could do TCDF range either way. But in this case, I'll just do, brain cramp. We want inverse T. The inverse T gives us the T value corresponding with the area, right? So I had a moment there. Anyway, so I'm going to put in inverse T of the area, which is 0.05 with 9 degrees of freedom, or you could put in inverse T of 0.95 with 9 degrees of freedom. All right. The inverse T asks for the area to the left of whatever value, but you'll see that regardless of what you put in a 0.05, it'll give me a negative number, but it's still the same absolute value. All right, so 1.833, I just dropped the negative. Or I can put in 0.95. So if it's 5% to the right, it's 95% to the left, gives me the same absolute value. All right, so what a lot of people do is they just put the alpha value in, and if it's on the left, they give it a negative. If it's on the right, they give it a positive. All right, that's an easy enough way of handling it. Right, so then the only thing that remains is to write the conclusion statement. There is sufficient evidence to reject the claim that, and I mentioned last time that I'd give you the conclusion template that we were using in class, and that you just fill in the blanks, but here it's, it's online, so it wasn't as easy to do. We state the null hypothesis in words. The null is that mu is equal to 5.75, and the mu represents the population mean gas price. So we would say sufficient evidence to reject the claim that the population mean gas price in California is $5.75 at the 0.05 significance level. And the second sentence addresses the alternative hypothesis. So the alternative, well, we get the check mark to say that that's a true statement. So I would just say, therefore, the claim that it is more than 5.75 is true. All right. So there was enough evidence to get rid of the null. That's what the first sentence talks about. All the particulars, what the null is and what the alpha value is. The second sentence addresses the alternative hypothesis. And somewhere in those two sentences, we should be answering the question that was asked. The question said, test the claim that the average gas price, all right, mean average, we're good, for California, addressed that it was California, is more than 5.75. So therefore the claim that it, referencing the gas price in California, is more than $5.75 is true. Right? And so that's a statistical approach for being able to demonstrate that. And this has got some quasi-real data, so take it for what it is. Just be glad we don't pay $5 and even like $5.01 here. Like we're down to we're in the low threes now. Like three. If you go to Fuelco over there, I think it's like 319, 329 maybe.
Where?
The Fuelco down the street, Virginia Road. It's by where the Dunkin' Donuts is, the John Franco's pizza place. That one you pay on the app, and it's always like 20 cents cheaper than all the surrounding gas stations. So you go right down the road, you pay like $3.59 at the Exxon, I think it is, but at the Fuelco, it's I think it's $3.39, it might be $3.29, but I always fill up there.